So this is f prime, and what does this graph tell me? Well, f prime at 1 is 0, so that tells me 1 is a critical number. That's what that tells me. F of at x equals 1, that's a critical number, which means on my original graph, this could be a maximum or a minimum. It could be neither, but it is a critical number because that's where the derivative equals 0. And then when I look at the part, I look at this part down here, that is below x. So what that tells me is this part below x tells me that f prime is less than 0 over here. So I'm going to write a note to myself that f prime is less than 0 from negative infinity to 1. It's less than 0. What does that tell me? That tells me that f is decreasing. In other words, this graph is going down on this interval. That's what that tells me. Wherever f prime is less than 0, the original function's decreasing. And then, if I look here, I look at this part, all of that part is above. That part is above, which tells me f prime is greater than 0 because it's above the x-axis. So f prime is above 0 from 1 to infinity. And what that tells me is f is increasing. F is increasing on that part. Now something that we just got in this unit is, if you look right here, f prime is negative. Over here, f prime is positive. So this tells me that f prime changed sign from negative to positive at x equals 1. Well, what does that mean to me? Well, that means that the graph was decreasing and started increasing at 1. So what does that tell me? That tells me there's a minimum at 1. There's a minimum value of this graph at 1 because this is the reasoning to have this. Now let's see what else this tells me. Since f prime is increasing, from here all the way up to here, f prime is increasing. Since f prime is increasing, what does that tell me? That tells me that f double prime, the slope of this is f double prime. That tells me f double prime is greater than 0 for all values. Now, what does that mean? Well, f double prime being greater than 0 for all values means that this graph is concave up everywhere. So this graph is also concave up. So what I want to do is start with an important point. Well, I know there's a minimum where x is 1. Now, I could put a dot anywhere I want on 1, and that's going to be a minimum. So just pick a place. Sometimes on a graph, they might tell you up here, they might say like f of 1 equals, it might say f of 1 equals negative 2. If it says this, you must put 1, negative 2 on the graph. You must put a dot right there. If it tells you a point, you must have that point on there or you lose the point. But this one doesn't say that, but I'm just going to make it up and say, all right, I'm going to put my f of 1 at negative 2. Again, I could put it anywhere I want on this one, but I need a point somewhere on this one because I know this point is my minimum. Okay, and I know this graph is decreasing to the left, so that means it's coming down and it's going up on the other side because of this stuff. And I also know it's concave up everywhere. So what I would do is I would have a concave up going this way, and I would have a concave up going this way. And that right there is a good enough example of this graph. It has my minimum at 1, 0. The graph is decreasing from negative infinity to 1. Then it's increasing from 1 to infinity. It's doing these two things. It is concave up everywhere. So that's good. Now, you do not have to have the graph exactly like mine. Maybe you put a dot here. Maybe you made the graph skinnier. But as long as it's decreasing and concave up everywhere, and it's a minimum at the 1, that's fine. I mean, you could put the dot anywhere. Oops, sorry. You could put that dot anywhere you want on one. I could put it clear up here somewhere. And again, you got to have it concave up and increasing, decreasing. So any one of these graphs would be okay for this information because the direction said draw a possible graph. Shouldn't it be -1? Oh, you're right. My graph is wrong. I looked at the number wrong. This should be -1. This should be -1. This should be -1. So all of these would be wrong because I did not do the graph right. Thank you. Thank you for straightening me out. So again, I should have had a dot over here somewhere going like this. And that would be okay. Thanks for getting that straight for me. Oh, a bunch of you are jumping on me. Yes, it should be -1. Good job of watching and checking me out. All right, we're going to do another one. We're going to do this one right here. So again, I'm going to look right there because this is f prime. So this is the one where f prime. Yeah, oh, let me go back over here real quick. Did I put a negative here? This should be a -1 right there also. All right, going on over here to this one. Now this one is 1. So f of 1, f prime of 1 here is 0. So again, now 1 is a critical number. Okay, now if I look at this, f prime is greater than 0 from -infinity to 1. Which tells me the graph is increasing, right? F is increasing on this interval. Okay, and then f is less than 0 because it's below over here from 1 to infinity, which tells me f is decreasing. Okay, now what else does this tell me? Well, this is positive, this is negative, so f changed sign. This time from positive to negative. So that means it was going up, coming down, which means there's a max. There's a maximum at x equals 1. Okay, so now 1 is the important point on this one. Okay, and then the slope of this graph is decreasing, f prime is decreasing the entire way, which tells me f double prime is less than 0, which tells me concave down. Okay, so again, 1 is the important point, so put a 1 somewhere. It's concave down everywhere because it's decreasing over the whole thing. And if you look, we're increasing to the left. So I got concave down, so I'm going to do this, and then concave down, I'm going to do this. This gives me the decreasing on that side. So there's a possible graph. So does that help you understand where everything's coming from? All right, great. Okay, I've also been asked to do another problem. Maybe more than one problem. Let me look here. I got to go back and got to move my chat up so I can see what else we got here. Okay, so on 5, 10, and 11, we want to do problem number 12. So let me find that. There it is. So we're going to do problem 12 on this. And I appreciate you guys jumping on me when I should have had a -1 there. That's awesome. It really lets me know. It's really good for you to find errors. That's why we got that error worksheet that I'd like you to do. I'm going to turn the light on so this picture gets brighter. Then I got to turn it off because I can't see the screen because the lights are so bright now. I changed all the lights over. I think they did that before you guys left. So we're going to do this problem number 12 here, which is a good problem. All right, so this problem number, man, I still can't see it very well. All right, I can see it on the paper though. It says Elena wants to get to the bus stop as quickly as possible. The bus stop is across the grassy park, 2,000 feet east and 600 feet north of her starting point. Elena can walk along the edge of the park of the sidewalk at a rate of 6 feet per second. She can also travel through the grass in the park, but only at a rate of 4 feet per second. Must be tall. Oh, dogs are walked there, so she must move with care to not get a surprise on her shoe. What path will get her to the bus stop the fastest? So we could say she's going to walk along the sidewalk, take a right, and walk along the sidewalk to get to the other end. That would be not cutting across the grass at all. Okay. I guess I'm on the wrong screen here. I have to go over here. Oh, I got that on. Let's move this out. So she could, one possible path she could take is she could go straight up the sidewalk, right over here to get to the bus, or she could do a straight cut right across the grass diagonally to get over here to that point right there. Or, as they have written here, she could start here and cut somewhere across the grass and then come straight down here to get to the bus stop. So we're kind of dealing with a problem here where distance equals rate times time, because we have a rate that she's walking, 6 feet per second on the sidewalk and 4 feet per second through the grass. And we have a distance she's traveling, 600 feet and 2,000 feet if you go straight up and across, right? So what we're looking for is we want to find what path will get her to the bus stop the fastest. Okay, so we're worried about time here. So time's what we want to get, and we want it to be the fastest. We want t to be the least amount of time to get where she's going, okay? So that means we're going to use this, and we're going to solve this for t. So t is going to equal d over r. So this is the problem that we want to deal with right here. All right, so we need to try to figure out what's going to be the best route. Well, if you recall, we're going to say this distance right here, and if we're going to cut across the grass. We're going to cut across the grass here. We're going to call this x from here to here, which would make this part over here 2,000 minus x. Okay? So if you look, we have a right angle right here. There's a right angle right there. So this would be some distance d right there. That'd be a distance d. Okay? So to get the total distance she's traveling, if she cuts across, let's put t for total. The total distance she would travel cutting across would be d plus 2,000 minus x. That would be the total distance she would cross, right? So if I wanted maybe I shouldn't put t because that might screw us up for time. We'll say sum. We'll put as for the sum of the distance cutting across, if that's 2,000 minus x. So this is the sum of her total distance right here, okay? So what we want to do is we want to get the total distance traveled. Let's see, we want distance divided by rate. So if you look, the total time that we're going to be dealing with here is going to be the distance she travels across the grass divided by rate 1, which we'll call rate 1 the grass travel, which is this 4. And then plus this distance she's traveling down the sidewalk divided by rate 2, which is going to be this 6 feet or 6 feet per second. This is going to be rate 2. So this would be the total time that she's traveling right here, these things. So what I want to do is I want to get all of this stuff in terms of x, okay, and rates. So to get this distance right here, if you look, we have a right triangle over here. This thing, let me use my highlighter. This thing right here is a right triangle. So from what I know about right triangles is I know that 600 squared plus x squared would equal d squared. So what that means is d would equal the square root of x squared plus, let's see, 1, 2, 3, 4, and 36. So there's the distance cutting across the graph. So we're going to say this is going to be x squared plus 360,000 divided by R1. Well, R1 is 4. Okay, that's at R1 plus 2,000 minus x divided by R2, which is 6. So I would probably, because we're going to have, we want to find, this is the thing we want to minimize. We want the fastest, which means we want the least amount of time. We want to minimize this time right here. Okay, so this is some t of x. Now what I would probably do is I'd probably put this 4 in the front and make it 1/4 here, and take this 6 and put a 1/6 here in front of this. Okay. You don't have to do that, but that's what I do. So then I'm going to rewrite this part and put it to the half power because I got to find the critical numbers here. So this is going to be x squared plus this squared. Oh, to the half power, my bad. To the half power. Okay, so we're going to do the derivative of this thing. So, because I want the critical numbers of this. Okay, so we got this deal right here. So we're going to do, keep the 1/4 in front. We're going to do the derivative of this, which is going to be a chain rule. So we got to take the power to the front, leave the part inside the same, subtract the power by 1. Then we got to go inside here and do the derivative of this, which is going to be a 2x. Okay, so there's the derivative of the first part. And then plus, we need the derivative of this part, so we leave the 1/6 the same. We go inside, the derivative of 2,000 is 0, and the derivative of negative x is -1. So I'm going to try to simplify this mess a little bit here. So let's see, I'm going to reduce this 2 with this 2. Those 2's will reduce. So let's see, we're going to have this is going to go to the bottom, so I got 1/4. And then down here, I've got the square root of x squared plus that. I'll tell you what, just to make it so I don't have to write as much, I'm going to change this back to 600 squared. And then plus, actually, it's going to be minus 1/6. So this is t prime. Now, I would probably want to get a common denominator is what I would do. So,
Mr. Woodrow,
yeah,
wouldn't the x go on top? Because you took out the 2, but you didn't
you're
take
right. This would be, there's an x here, right? There's an x right here. Thank you. That x would stay up here on top. Thank you. All right, so now, and if you're going to talk, if I screw up, talk to me because I'm not standing by the computer. I'm standing over here by the screen because I can't read this very well because it's kind of dark on my screen. Hope it's better at your place. So I would probably get a common denominator here. So I would 12 is the common denominator between these. So I'd get a multiply by 3/3 and get this. And then over here, I need to get the multiply by 2 to get a 12. And then I'm going to have to multiply by this square root part to get the common denominators. So to save myself some time, I have common denominators, so I can take this top part and put it all over one denominator. So I'm going to do that. Okay, so now I want to find my critical number. So I want to know where t prime equals 0, which is going to be where does that top part equal 0? And where is t prime going to be undefined? Okay, well, that's where this bottom part would equal 0. Okay, so what I see right now is any number that I square, any number I square is going to be 0 or positive, right? So if I square any number and it's 0 or positive and I add a number to that, that means there is no place here where this is ever going to equal 0. Now, if you go through and solve this, you're going to get a negative inside your square root, which is going to tell you there's no answer here. So I get no critical numbers from this. So this is where my critical numbers come from. So I got to solve this thing by adding this over here. And then you want to get rid of the square root. So we're going to square this side and we are going to square the other side. I hope this works out pretty because I don't know if it will or not. So I got 9x squared here, and over here I got 4 times x squared plus 600 squared. I just take that part out of the radical. All right, so I'm going to distribute that 4, right? So I'm going to get 9x squared is going to equal 4x squared plus, let's see, what's 36 times 4 here? 4 carry 2, 144. So I got 144. Let's see, and I have 1, 2, 3, 4 zeros. So I believe that's what I get there. If somebody has a calculator, would you take 600 squared times 4 and see if I did that right? I hope so. So then I get 5x squared is going to equal this number.
It's right, by the way.
Okay, and then take that number and divide it by 5. Let's see, 5 goes into 14 twice. Then it'd be 40, 8 times, 8 times again. Is that right? Is that what you get when you take 1,440,000 divided by 5?
Yeah.
So x is going to be a positive or negative 288,000, the square root of 288,000. That's what I get. Now, I want to remind you, I'm going to draw this picture real quick over here. So we're starting here, and we got this rectangle. And this is 600. I think this was 2,000. And we may be cutting across here to get to this bus stop over here, right? Now, if you go negative, remember this was x right here? This was the x. If you go negative, you'd be going that way. Is there any chance that going that way would be fastest? And the answer would be no. So the only number I need to worry about is this number right here. So I'm going to do that. I could go 0 across, go straight up here and over. You know what? We'll just do EBT. Okay, so I got 1 and the x is 0. So I'm going to use EBT because this is a continuous graph, because there's no places this is 0. So I'm going to say x could be 0, where I stay on the sidewalk the whole time, okay? X could be where I cut across, that's this critical number right here. Or x could be that I go straight across this way where x is 2,000. Those are my endpoints for x, 0 or 2,000. And now I want to do this for to minimize my time, which is this function right here. I'm wanting to minimize this one. So let's minimize this thing. So I'm going to write that function down here again. So I got t of x equals 1/4 times the square root of x squared plus 36. I'm going to make that 600 squared. And then it was plus 1/6 times 2,000 minus x. So I think I'm going to cheat here. We can plug 0 in and get it pretty quickly. So if I do t of 0, that's 0, right? And then the square root of 600 squared is just going to be 600. And then it's going to be plus 1/6 of 2,000. So I guess I am going to use my calculator here because I want to get this done because it's been going longer than it should have. So that comes out to be 483.333 repeating on my time. Now, just to remind you what this time is up here, this was 4 feet per second, so this would be seconds. So this would be, if you follow the sidewalk, it would take you that long to get there. Then I'm going to take this square root of 288,000 and plug it into this thing. So I'm going to go ahead and do that on my calculator here. So let's see, we got. And you guys might do it at home to make sure I don't type something wrong in. Oh, shoot. Okay, that comes out to be, I wonder if I typed something. Let me check my typing because I thought that was going to be my best answer, but maybe not. Oh, I left off something up there, darn it. Okay, so this one comes out to be 445.137 seconds. And then I'm going to stick 2,000 in here. That's cutting straight across. I hope you see that gets rid of this one because you're not walking on the sidewalk at all. So we got to put 2,000 into this one. So let me do that. Nope. And that one comes out to be 522.015 seconds. So we wanted the least amount of time, which is this one. So what we would say is you would write the least amount of time would be if the person cut across the grass such that x was the square root of 288,000, which would make the total time 445.137 seconds. So that is a majorly difficult problem, but it is doable. And anybody else? I hope somebody else checked that. Does anybody else have any problems you'd like to see?
So just to clarify, that means
Yeah.
the grass path was the fastest?
Cutting
Or was
across
that-
the grass. Okay, here's what this says. Okay, if you look right here, this is x, right? The x is these. So the cutting across the grass such that that x right there would be a square root of 288,000 feet. I think it was feet up there. So if that x is a square root of 288,000, that's where cutting across would be the fastest way.
Why'd you use 2,000 for the last one? Because isn't 2,000 the side
Okay,
not the hypotenuse.
do you remember EVT? EVT says that either the endpoints or the critical numbers can be your max and mins, right? So if I said X is 0, going back to my picture, if X is 0, that means I stay on the sidewalk the whole time. Okay? That's what that means. If X is that square root of 288,000, that means I cut across and then down. If X is 2,000, that's this whole thing right here, right? X is 2,000, that is me cutting across. So basically 0 is less than equal to X is less than or equal to 2,000. Those are my endpoints for X. My interval is 0 to 2,000 for this. It's either 0 and I can walk the sidewalk the whole way, or it's 2,000 when I cut straight across diagonally. So if you remember, by EVT, you're guaranteed to have a maximum, an absolute max and an absolute min that is either a critical number like this one, or it's an endpoint like this one or this one. These are the endpoints for X. Anybody else got a question? Somebody said, why wouldn't you use a 45, 45, 90? Well, you're not guaranteed that it's going to be a 45, 45, 90 because it's different rates. The rates in the grass is different than the rate walking on the sidewalk. So there's no guarantee that it's a 45, 45, 90. And as a matter of fact, this one is not a 45, 45, 90. Anybody else got any questions? Okay, that's a pretty tough problem. I will, again, tomorrow you've got Zoom from 9 to 9:45. If you want to come and ask questions, you do not have to. Try to work a lot on that review to check to see if you know how to do everything on there. And then Monday we'll go over the review questions and or I'm going to have to, I don't think I put the error problems on the sheet, so I'm going to stick those error problems on Monday, and I'm going to see if I have a key for that. I think I sent out yesterday, there's more than one mistake on that, on the three big theorems, so don't do that at all, because I worked through that yesterday, and I sent the guy an email that I got it from, and he said that he's going to have to go back through it later, and we may go over that when it comes back to reviewing for the final after spring break. Okay, so you guys have a great weekend. I'm not seeing any more questions pop up. Have a great weekend. Stay out of trouble. Do what's right, not what's popular, and I'll see some of you tomorrow and the rest of you on Monday. Take care.
Mr. Woodrow, can you